In one of the most monumental discoveries of the 20th century, we learned that the universe is not simply a static, unchanging background, but rather that space itself expands as time marches on. It's as though the very fabric of the universe itself is stretching, so that distant objects get farther and farther apart. We see this phenomenon in all directions and in all locations in space. Nearly 100 years after it was all worked out, it's still a puzzling, counterintuitive phenomenon even for experts in astronomy and astrophysics. It's only natural to wonder if the universe is expanding, what exactly happens to the fabric of space itself while this process occurs. Is the space itself stretching as though it's getting thinner and stretched out? Is more space constantly being created as though it were filling in the gaps that the expansion creates? And if the universe has been expanding for all this time, what is it that the universe is expanding into? Are we expanding along with the universe? This is one of the toughest things to conceive of in modern astrophysics. Fortunately, the latest data from James Webb are providing new insights that help shed some light on these mysteries. Join us as we explore what's exactly going on. For theoretical beginnings, the starting point of our conversation has to be general relativity, our modern theory of gravity first put forth by Einstein. General relativity, at its core, is a framework that relates two things that might not obviously be related: the amount, distribution, and types of energy, including matter, antimatter, dark matter, radiation, neutrinos, and anything else present throughout the universe, and the geometry of the underlying spacetime, including whether and how it's curved, and whether and how spacetime itself will evolve. If we inhabited a completely empty universe or a universe that contains nothing within it at all, no matter radiation or energy of any form, we'd get the flat Newtonian-like space we're intuitively used to, something that's uncurved and unchanging. But what if we then considered the absolute simplest case of a non-empty universe? If instead we were to put down a point mass in the universe, we'd find out that space was curved in a particular way, such as in Schwarzschild space. Any test particle that we put down onto our universe would be compelled to flow toward that mass, following a particular trajectory. And if we were to then make our physical situation just a little bit more complicated by putting down a point mass that also rotates, we'd get space that's curved in a more complex way according to the rules of the Kerr metric. These spacetimes are clearly much more complicated than a spacetime that's simply flat. However, they are still static in the sense that any distance scales you might include or measure, like the size of the event horizon or the distance between two arbitrary points within the spacetime, don't change over time. If we could somehow exit a universe with this spacetime and return to it later, whether a second, an hour, or a billion years later, the structure of the spacetime would be identical irrespective of when we return to it. In spacetimes like these, there's no cosmic expansion that's present, there's no change in the distance or the light travel time between any points within the spacetime, with just one or fewer sources of matter inside and no other forms of energy. These model universes really can be static, expansion, and contraction of the universe. But it's a very different game when you choose not to put down isolated sources of mass or energy, but instead to fill your universe uniformly with stuff. In fact, the two criteria we normally assume about our universe and which are strongly validated by large-scale observations are called isotropy and homogeneity. Isotropy tells us that the universe is the same in all directions. Everywhere we look on cosmic scales, no direction looks particularly different or preferred from any other. On the other hand, homogeneity tells us that the universe is the same in all locations. The same density, temperature, and expansion rate exist to better than 99.99% precision on the largest scales. As far as we can tell, our universe, on large cosmic scales, is indeed both isotropic and homogeneous. In this case, having a universe that's uniformly filled with some sort of energy, the rules of general relativity not only mandate that the universe must evolve, they tell us how. The equations that govern the evolution of the universe are known as the Friedmann equations, derived by Alexander Friedmann all the way back in 1922. The space-time fabric of the universe, if it's uniformly filled with one or more types of matter and energy, must expand or contract according to these equations. The mathematics tells us with no ambiguity that this must occur. But what exactly does expansion or contraction actually mean when it comes to space itself? You see, space itself is not something that's directly measurable. It's not like we can go out and take some space and just perform an experiment on it. Instead, all we can do is observe the effects of space on observable things, things like matter, antimatter, and light, and then use that information to figure out what the underlying space itself must be doing to cause those effects. For example, if we go back to the black hole example, although it applies to any mass, we can calculate how severely space is curved in that black hole's vicinity. If the black hole is spinning, we can calculate how significantly space is dragged along with the black hole due to the presence of the black hole's angular momentum. If we then measure what happens to objects in the vicinity of those objects, we can compare what we see with the predictions of general relativity. In other words, we can actually perform experiments to determine whether space curves in the way Einstein's theory tells us it ought to, in a wide variety of ways. As soon as the first conflict arises, as soon as a single observation is inconsistent with Einstein's predictions, we will have a compelling case for extending the theory of gravity beyond Einstein's general relativity. But a full 109 years after general relativity was first put forth, the day has not yet arrived. To an incredible level of precision, every observation matches and agrees with general relativity's predictions. Light blue shifts when it enters an area of extreme curvature and red shifts when it leaves. This gravitational redshift has been measured for stars orbiting black holes, for light traveling vertically in Earth's gravitational field from the light coming from the Sun, and even for light passing through growing galaxy clusters. It's also been measured right here on Earth, as light red shifts when it travels upward in Earth's gravitational field and blue shifts when it travels downward, closer to Earth's center. Similarly, other predictions such as gravitational time dilation, the bending of light by large masses, and the precession of everything from planetary orbits to rotating spheres sent up to space, have all spectacularly agreed with Einstein's predictions. But what about the universe's expansion? When we think about the expanding universe scientifically, the question we should be asking ourselves is what observably is changing about the things we're capable of measuring in the universe. After all, that's what we can physically predict, that's what's physically observable, and that's what will inform us as to what's actually physically occurring. Anything else is us placing a veneer, a mask, reflecting the limits of our own intuition atop what we actually understand about reality. The modern picture of the expanding universe. The simplest evolving quantity we can consider in an expanding universe is density. If our universe is filled with stuff, then as the universe expands, the volume of the space that this stuff occupies will increase. We normally think about matter as the stuff. We're thinking about matter at its simplest level, a fixed amount of massive stuff that lives within space. As the universe expands, the total amount of stuff remains the same, but the total amount of space for the stuff to live within increases. For matter, density is just mass divided by volume, and so if your mass stays the same while your volume grows, your density should go down. When we do the general relativity calculation, that's exactly consistent with what we find for matter. But even though we have multiple types of matter in the universe, normal matter, black holes, dark matter, neutrinos, etc., not everything in the universe is matter. For example, we also have radiation, quantized into individual entities like matter but massless and with its energy defined by its wavelength. As the universe expands and as light travels through the expanding universe, not only does the volume increase while the number of particles remains the same, but each quantum of radiation experiences a shift in its wavelength toward the redder end of the spectrum, longer wavelengths. This redshifting effect is how the expanding universe was first detected and shows up in every galaxy and quasar we measure beyond our own local group. Meanwhile, our universe also possesses dark energy, which is a form of energy that isn't in the form of particles at all but rather appears to be inherent to the fabric of space itself. While we cannot measure dark energy directly the same way we can measure the wavelength and energy of photons, there is a way to infer its value and properties by looking at precisely how the redshifting light from distant objects evolves as a function of distance. Remember that there's a relationship between the different forms of energy in the universe and the expansion rate. When we measure the distance and redshift of various objects throughout cosmic time, they can inform us as to how much dark energy there is as well as what its properties are. What we find is that the universe is about 2/3 dark energy today, and that the energy density of dark energy doesn't change as the universe expands. The energy density remains constant. When we put the full picture together from all the different sources of data that we have, a single, mostly consistent picture emerges. Our universe today is expanding at somewhere around 70 kilometers per second per megaparsec, which means that for every megaparsec or about 3.26 million light-years of distance an object is separated from another object, The expanding universe contributes a red shift that's equivalent to a recessional motion of 70 kilometers per second. That's what it's doing today, but by looking to greater and greater distances and measuring the red shifts there, we can learn how the expansion rate differed in the past and hence what the universe is made of not just today but at any point in history. Today, our universe is made of the following forms of energy. About 0.8% radiation in the form of photons or electromagnetic radiation, about 0.1% neutrinos, which now behave like matter but behaved like radiation early on when their mass was very small compared to the amount of kinetic energy they possessed, about 4.9% normal matter, which includes atoms, plasmas, black holes, and everything that was once made of protons, neutrons, or electrons, about 27% dark matter, whose nature is still unknown but which must be massive in clumps, clusters, and gravitates like matter, and about 68% dark energy, which behaves as though it's energy inherent to space itself. If we extrapolate backward based on what we infer about today, we can learn what type of energy dominated the expanding universe at various epochs in cosmic history. And if you can measure the expansion rate today and how it's evolved over time, you can determine what's in your universe right now as well as what it was like in the past and how it will evolve into the future. With good enough observations, we can determine our ultimate fate. James Webb deepened the crisis in cosmology. However, based on multiple observations of stars and galaxies from James Webb and Hubble, the universe seems to be flying apart faster than our best models of the cosmos predict it should. Evidence of this conundrum has been accumulating for years, causing some researchers to call it a looming crisis in cosmology. As Nobel Laureate Adam Rees, who led the latest effort to test the anomaly, said, "The universe seems to throw a lot of surprises at us, and that's a good thing because it helps us learn. If the Hubble tension really does reflect our physical reality, then explaining it will probably require adding another item to our list of the universe's fundamental ingredients." One of the leading theoretical contenders, called early dark energy, proposes that about 50,000 years after the Big Bang, there was a brief flare-up of dark energy. In principle, a short blip of extra dark energy could alter the expansion of the early universe enough to resolve the Hubble tension without messing too much with the standard model of cosmology. But in the process, cosmologists' estimates for the age of the universe would fall from the current 13.8 billion years to about 13 billion years. According to Mike Boylan-Colchin, an astrophysicist at the University of Texas at Austin, there's a lot of questions about why you have to introduce this one new thing that just shows up and disappears. That feels a little funny. But we're in a place where, if these things are really that discrepant, maybe we have to start looking in the funny corners of the universe. In a brand new study published in the journal Classical and Quantum Gravity, Dr. P.K. Shurish and his colleague from the University of Hyderabad, B. Anupama, proposed a solution to align these disparate results. They underscored that physicists infer the Hubble parameter indirectly, employing our universe's evolutionary model based on Einstein's theory of general relativity. The team argued for revising this theory to incorporate quantum effects. These effects, intrinsic to fundamental interactions, encompass random field fluctuations and the spontaneous creation of particles from the vacuum of space. Despite scientists' ability to integrate quantum effects into theories of other fields, quantum gravity remains elusive, making detailed calculations extremely difficult or even impossible. To make matters worse, experimental studies of these effects require reaching temperatures or energies many orders of magnitude higher than those achievable in a lab. Acknowledging these challenges, Shurish and Anupama focused on broad quantum gravity effects common to many proposed theories. Their theoretical exploration revealed that accounting for quantum effects when describing the gravitational interactions in the earliest stage of the universe's expansion, called cosmic inflation, could indeed alter the theory's predictions regarding the properties of the microwave background at present, making the two types of Hubble parameter measurements consistent. Of course, final conclusions can be drawn only when a full-fledged theory of quantum gravity is known, but even the preliminary findings are encouraging. Moreover, the link between the cosmic microwave background and quantum gravitational effects opens the way to experimentally studying these effects in the near future. What is the universe expanding into? Back to the expanding universe, today we have every reason to think that our observable universe, whose cosmic horizon is set by a combination of the expansion rate, the speed of light, and the amount of time that's elapsed since the Big Bang, only represents a small fraction of a larger, more complete, unobservable universe. The observable universe will continue to grow as light from distant regions arrives, eventually revealing more than double the current visible volume. The unobservable universe might be infinite, making it meaningless to ask what it expands into, as infinity plus or multiplied by infinity remains infinity. Cosmic inflation suggests our universe is just one region where a Big Bang occurred, with other regions experiencing similar events in an inflationary multiverse. However, our universe is not expanding into this multiverse. It simply encompasses all that exists with no outside to expand into. This means the universe's expansion is a property of space itself. Many galaxies, like those in the Virgo cluster, don't follow expansion laws exactly due to gravitational binding, which creates peculiar velocities. Only unbound systems experience universal expansion. Locally, structures bound by gravity or electromagnetism, such as atoms, humans, and stars, do not expand. The largest bound structures in the universe are between 1 and 2 billion light-years. Beyond these, expansion becomes significant. This understanding helps clarify that while space expands, it doesn't do so into anything else. Thus, the universe is expanding into itself, governed by inherent spatial properties.